do it again, this time by. Let's do cofactor. So remember cofactor? First look at the checkerboard matrix. And we're going to go say middle row or middle column? So for the middle row, I go -1 times something, plus 6 times something, minus 8 times something. So when I have that -1, so the -1 came from this part, is I cross out one's row and one's column, and I'm left with 2, 3, and 4. And then for the 6 came from that middle one, cross out 6's row, 6's column, 1, 2, 0. And then finally, for the 8, cross out 8's row and 8's column. It's 1, 2, -2. So this is -1, 0 minus -12, plus 6 times 0 minus -6, minus 8 times -4 minus -4. So this is -12.
36.
Was it 36?
Yes. 0.
And 0. And -12 plus 36 is 4. Which I was hoping it was, because I already calculated this at 24. I want to make sure that I'll come back to the Saras's rule. We have time. So I want to make sure we talk about these.
Basically determine the integral time.
Yes, exactly. So this is the AB minus BC. Pretty sure that's.
That's called a cofactor?
That is called cofactor. So I'm going to skip Saras's rule.
So what is Kramer's rule?
Kramer's rule is a way to use determinants to solve a system of equations.
Which you find a determinant by doing cofactor.
I know 3 ways to do a determinant. So Kramer's rule just says if you put these determinants together in this way,
Right.
you'll have a value for x. And then you can find the determinant any way you want. You can do it by elementary operations, you can do it by Saras's rule, you can use a shortcut.
I learned that.
That's one of many ways to find it. Yeah, I'm cool with the cofactor expansion. Kramer's rule is guided.
It was like a 13-point problem.
I'm going the way it's determined with diagonals.
Yeah, that's Saras's rule for the 3 by 3.
Okay. And that's like a simplified version of Kramer's rule, right? Isn't that?
No,
how
Kramer.
it comes from? Sorry, not Kramer's rule, but the cofactor expansion, right? Like if you.
Okay, the cofactor expansion will work for any size matrices. That copy of the molar only works for 3 by 3.
But it's the reason it works. Like you can prove that it works with the cofactor expansion, right? That's kind of where it's derived from.
I see what you're saying. But
That's
that's
what it seems like.
Yeah,
If
no.
I would have to prove that. That's how I feel.
That's one way to prove it.
Okay.
So usually the determinant's defined, if this was a math class, I would be defining determinant very differently.
Okay.
It is not a math class. It's pre-engineering.
What?
No, seriously, it's, how many math majors are here? Yeah, 2, 3, excellent, 4, okay.
What?
4 even. So right, I'm not teaching a math class, I'm teaching a class to get kids ready for their STEM.
That's not what I signed up for.
I didn't know that. I didn't know
Yeah,
that.
no, it's, I guess the way I think about it is your first 2 years in math school, it should be just about developing the intuitions. So knowing the determinant is an area expansion factor. And then it's your last 2 years as a math major that you should be worried about the proofs and how it all goes together. And the engineers also need to understand how it all hangs together. Was it?
I didn't know there were only 2 math
3?
Oh, 3.
So again, if I was teaching this class to math majors and getting you ready for upper division, if I knew you were all going to upper division linear algebra, I'd be doing something different with the determinant. But you're going to see the real mathematician's definition of determinant when you take your upper division linear algebra classes. So I've got written down the colors. We'll make this square brown. Okay, so this square, remember one way to think about a matrix is it's going to take vectors from an input space, turn them into vectors into an output space. We talked about how Smiley would get mapped. Now we're going to see where this square gets mapped. So this square is like that. It's, where does this black vector go? It's 1, 0, goes to where? 1, 2. And remember, that's, is that right? No, like 1, 2. So 1, 0 is one of those special vectors. The matrix times 1, 0 just extracts out the first column. And where does 0, 1 go? So then what you're going to see is this part would go here, here. So the shape is a parallelogram. And there's a complicated geometry way to get the area of that parallelogram. What do I know about determinants?
It's the area.
Area expansion factor. So the determinant is 1 minus 4, which is negative 3.
You found the typo?
Oh,
There, it says it's negative 10 here.
oh, thank you.
So there's another one.
Cool. And asymptotically approaching perfect solutions. Next semester, students, thank you. I don't know how it happened, but I got another linear algebra class next semester. Missing. Oh, usually, because I get 2 this semester. People like to teach it, so.
Oh, okay.
We
Because
should.
it's right there.
Yeah, no, yeah, I teach all linear algebra all day if it was me. Okay, but what does a negative determinant mean?
It's flipped as well.
Yeah, what that means is from axis 1 to axis 2 is a counterclockwise rotation. And in the image, it's hard to see with this shape, but it really went through the mirror. So this area is 3, and the negative is the fact we got is reflected, the mirror image.
So you would not call the area negative.
You're right.
Oh.
Yeah, sometimes we want signed area, sometimes we don't.
I guarantee that I'm gonna end up writing
I
things.
don't-
So is that item
Oh, area, A for area. Oh, actually, let's back up. What's the area of this guy?
1.
And then the fact that the determinant is negative 3 means the areas go up by the magnitude of that. So every area is 3 times bigger. And then, the last part of this question is I've got this square, which has -1 as the bottom corner, and 1, 1 as the top corner. What's the area of this guy?
4.
It is 4. It's 2 this way, it's 2 that way. And when I come over here, I'm going to get some very cool parallelogram. What's the area of that going to be?
12.
It's going to be 12. Exactly. So the determinant measures how much, by what factor, the area changes. Good. I'm going to briefly go through 7.4. And the 7.1, the diagonalization, I think is pretty mechanical. It's just a series of steps to get the SDS inverse factorization. There's a series of steps for the SRS inverse and for the SJ S inverse. So my other job is I teach 18-year-old kids who are their first semester in college. And I gave a midterm today.